Hello, everybody. My name is Alberto. I've been working for CSCS for a little over 3 years now. And for around 2 years and a half, I've been working on container solutions for HPC. And today it will be my pleasure to share with you our latest efforts, which we called Sarus, about a container engine for HPC. So I start with a little bit of a quick introduction to containers, with just a couple of slides, nothing. Then I will talk about the requirements that we have put together at CSCS for what we would like to see in a container solution for HPC. Then I will present Sarus and elaborate a little bit more on so-called OCI hooks, which are a very important component in our architecture, and then I will present you with some performance numbers. So containers can be defined in a lot of different ways. There are many different things for many different people, but for our purposes, we can define them as isolated environments where you can run applications, services, computing, basically processes. The contents of these isolated environments are provided by an image, which already includes all the software dependencies. So really, the container is this entity that is self-sufficient and is really tailored around a single application. At the current state of the art, containers are prescriptive, they are portable, so you can deploy them wherever you have a compatible container engine. They're easy to build and very quick to deploy, especially compared to a virtual machine. And here we have a kind of a classical diagram representing the difference between a container and a virtual machine. The experience, even though the technology is quite different, the outside experience is quite similar. But the difference boils down to the fact that the container does not virtualize the hardware, it does not virtualize the kernel, you're just reusing the kernel from your host system, and you do not have to provision it, so it has all sorts of operational advantages. When we talk about Linux containers specifically, they all basically reuse the same basic building blocks. Nobody is inventing a container technology which is completely on its own and different from all the others. Because the containers, they all rely on these abstraction features provided by the Linux kernel, which are called namespaces. You may have heard about them. And if you really want to know what makes containers tick at the low level, I cannot recommend enough this series of articles on Linux Weekly News, but it kind of gets on the technical, so but it's a great read. But while the base technology is similar, there are a lot of details to get right, a lot of choices along the way to assemble a complete container solution. So these different decisions, different use cases led to the birth of several container products. Here you have the main one, we can say. I think it's most of them, of the popular ones. I'm sure you recognize some of them. We have Docker, which is the de facto standard, is the most popular solution. Then we have the Rocket, Podman, which is kind of a new kid on the block. Looks very promising. And then we have the HPC-focused container runtimes, which Singularity, Charlotte Cloud, and Shifter. So we have been tinkering with containers at CSCS for quite some time now. We started in 2015 with an early Docker evaluation for GPUs. Then in 2016, we decided to work on Shifter, and we extended it by giving it the possibility of obtaining native performance from GPUs and specialized MPI implementations, and we deployed Shifter in production on our flagship system, PITS-Dint, in 2017. Then in 2018, we decided to re-implement and rewrite some internal components of Shifter in order to have a better experience both inside as operation and outside on the user-facing side. So we have a Docker-like command line interface, and we also have this image manager which works better than the Shifter's original image gateway service. And we proceeded to deploy that in production, this Shifter NG flavor in production about a year ago. It was April 2018. And then from basically fall 2018 to right now, we dedicated ourselves to the development of Sarus, which is what I'm talking about today. So you see that you have matured a respectable amount of know-how, I would say, in this time frame. So we were able to synthesize and to express what is important for us in a container engine or a container solution that we would like to see on PITS-Dint and on a computer of similar kind. So of course, the first requirement is that it has to be suitable for HPC. And we mean it has to work with diskless compute nodes. This is something that Docker, for example, still struggles with. It has to be compatible with the presence of a workload manager and respect the constraints assigned from the workload manager. It has to be parallel file system friendly, so not to degrade the performance of a parallel file system. And of course, be adequate for a multi-tenant system. Here is no privilege escalation, but it's also important to respect the user identities and file permissions when you're accessing shared resources. We want pluggable vendor support, meaning that we, as in either CSCS or for some other developer of a container solution, we should not run after vendors in order to enable their technologies, their proprietary high-performance technologies, to work inside containers, because this requires a lot of effort. It's very time-consuming, both not just to enable a new technology, but also to maintain these technologies as the systems and the software move forward. So we would really like vendors to take care of that. Through a set of pluggable software, like think browser plugins, you just have an independent little program that is called by your container solution, and it does what it needs to do inside in order for the container to work with a high-performance infrastructure. Obvious examples for us are GPUs. I'm sure you know we have a quite big GPU computer. A Cray MPI, because we have the dedicated Cray network interconnect, RDMA, stuff like that. User experience, of course, user experience is very important. And in this regard, it is undeniable the advantage that, the popularity that Docker has achieved, to the point that for some people, containers are almost a synonym with Docker. So we really see an advantage in providing a consistent user experience consistent with the one from Docker. So the users, when they start using containers on the HPC system, they already find themselves in a familiar environment with a familiar interface, and can get up to speed faster and spend more time in using the software than in learning about the software. So this for us means Docker-like command line interface, the integration with Docker registries, the capability of pulling stuff from Docker Hub, for example, and a writable container, the ability of really writing files inside the container. This is something that not all current HPC container software allow you to do. Administrator experience. We care about our system administrators. Always give credit to your system administrators. They're a good bunch of folks. So we want to simplify their life, not complicate it. So it should have an easy installation. So it is easier to deploy new versions in production. And we also want to be able to tailor the installation of the container software to the hardware of a specific machine. So if you have GPUs or if you have another type of accelerators or one network or the other, InfiniBand, Cray, or whatever. And then, of course, it should have a low maintenance effort from the software and code side as well. So we really look favorably to reuse of third-party technology and community efforts. So putting these requirements together to the current state of container solution here, we took Docker and the other, some of the more popular ones were Docker and LXC, which is more general purpose, and the 3 HPC-focused container runtimes. So Docker, of course, has the best experience, is the most popular, but it really doesn't play well with HPC as of now. What happens in the future, we don't know, but as it is now, it's very difficult to make it work on an HPC system, and it doesn't expose the possibility of plugging in stuff. Singularity is probably the most popular of HPC focused container solution, but it doesn't offer plugins, and from a user experience side, they kind of tend to reinvent the wheel. They try to re-implement the whole Docker ecosystem without being Docker. So we will like something different. And there are also some security concerns, long-standing security concerns about Singularity. Charlie Cloud, it is a very capable solution, especially from a security and system administrator point of view, because it is completely user side. System administrator doesn't have to do anything, but it really requires a proficient user in order to set up the container, and they also do not expose plugin interfaces. Shifter is the one we've been using for a couple of years at CSCS. It's good. It runs what we expect from it, but again, no really plugin support, and has quite a complex architecture, so maintaining it in operation sometimes is a bit of a hassle. LXC, very feature-rich container solution, but it has a lot of features, but most of all, they're not quite what we would like. So, for example, it exposes plugins, but they have to be, but they're not standard plugins. They have to be written specifically for LXC. User experience, it's focused on itself. It's very on workflow and stuff like that. And runc, it's a low-level runtime. It's used internally by Docker. It's a small executable program that creates the container. It exposes a standard interface for plugins, and being a single executable is really easy to deploy, but it's really low level. So in order to fire up a container from that requires quite a lot of effort. You have no image management, no nothing, no help from. You have to set up all the things yourself. So as you can see, there is basically nothing around that that satisfies completely what we would like to have. And so we talked about it, and we decided to try our own. And so here we come up with Sarus. Sarus is a container engine, so at the same level of Shifter, Singularity, Docker, specifically developed with the requirements of HPC. in mind. It is compliant with open standards, so we can reuse community efforts, and it's based around an extensible architecture. So it is easier to maintain and more future-proof. So if we start to compare it bit by bit with the others, it is suitable for HPC. We mount the container image in a way that is easy to distribute across the compute nodes and doesn't thrash the parallel file system, compatible with a workload manager, and is able to expose native performance from specialized hardware through vendor extension. Speaking of vendor extension, Sarus uses the interface of OCI hooks. I will talk about this more later. I will explain it in more detail. So we're able to, for example, integrate NVIDIA components in order to enable GPUs to work natively inside containers in a completely transparent way, both from a user side and from a system administrator side. User experience, it has a Docker-like command line interface, integration with Docker registries. We overlay FS, so you can work in the container, you can temper whatever you like. And we also preserve identity and file permissions when accessing the parallel file system or share a file system with a scratch or the user's your home folder. From the administrator point of view, it is a single executable binary. The plugins, the OCI hooks, allow select and dedicated functionalities to be enabled on a per system basis. So you can really only have the dedicated features that you want on the machine that you want them. And you can enable and disable them. It's just a configuration tweak. And we reuse the low-level runtime of runc to spawn the container, so we can leverage on all the features of the experts from the broader container community that they pour into this solution for security and features. And we made it as standard compliant as we could be, and reuse a lot of open source technology. So we reuse we do not re-implement a core runtime. We only take care of the HPC related stuff. Reuse third-party libraries. We are compliant with open standards, and it's quite well tested. Yes?
I ask a question on how many field tests have you made your assessment?
What do you mean, how many field tests?
How many HPC machines are using Sarus?
Well, for now it has been only within CSCS, so we have...
How can you then make this assessment while the others are around the world? And you are tough with your assessment, and here you just put green, green, green.
Well, it's because we made our assessment, for example, Shifter. We have operated basically most of the machines we tried, most of these solutions we tried ourselves. Singularity is provided on PITSDynth, since we support it since quite some time. Shifter, we had it in 2 years.
Yes, but have you used ours on Summit?
Well, right now...
I don't know where.
Sarus is very, very young. It's a newborn baby. We would like to make as wide as assessment we can make, but for now we only tested inside CSCS. So basically, the green ones here is because we get it expresses the fact that we get everything that we would like to see in a container software like this. Regarding the CLI, so it's one of the most important aspects for a user. You can see that we got it as close as we could with Docker, so it should be really easy to pick up. And this is a bird's eye view of the architecture. So you can see we have the configuration that's based on JSON, the user input, and Sarus is able to communicate with a cloud registry or a tar file and store the container image in the parallel file system. And then when you request a container to be run, Sarus retrieves the parallel from the parallel file system the image, it repairs the container bundle, and then hands it over to a standard runtime. The standard runtime, in turn, can use the external component for customizing the container, and then it just fires up the container process. So I've been throwing around these OCI word a little bit, and especially the focus on OCI hooks, which is kind of a highlight of Sarus, especially in the HPC landscape. There is no one else that exposes the possibility of using these hooks. So let's talk a little bit more about those. First of all, what is the OCI, if you're not familiar with it? Well, OCI is short for the Open Container Initiative. It's an open, I read verbatim, an open governance structure for creating open industry standards around container formats and runtimes. It was formed, so it's an open organization for open standards. It was formed in 2015, I believe, by industry leaders in the container sector. So Docker is there, Red Hat is there, CoreOS is there, SUSE, Google, Amazon, you name them. The big names are all there. And these guys put together a list of specifications that basically define how a standard container how an image should be made of, how an image should be distributed across the internet, and how a container should be assembled and run. So basically, this means that since Sarus respects these specifications, these interfaces, it is compliant both from the distribution point of view and from the runtime point of view. It basically means that this is a standard component that can be swapped out and replaced with another standard runtime as we see fit. Right, for now, there is a reference implementation by the OCI themselves. It's called is the RunC that I already talked about. So just by doing that, we reduce the development effort of having to figure out all the low-level intricacies of getting namespaces right, C groups, container isolation, and that. But we also get the benefit of the updates of security and features that the OCI will develop over time. And if eventually in the future another standard compliant runtime fires up, there are one or two interesting stuff, but they are very in the embryonal stages. We can just swap them out and have the runtime that we need, that we think it's better for us. And then there is another interface, which is the thing that we see a lot of promise into, which is the interface between the runtime and these plugin components. There is a part of the OCI runtime specifications that defines this interface to plug in external programs to customize the container without either the container runtime or the driving container engine to know what is it doing. So, for example, our hope is that hardware and technology vendors will pick up and provide these specific extensions for their technology in order to have them work within containers, without so having the maximum return with the minimum effort, both for HPC centers and the users. So, of course, the primary use case for these plugins is the high-performance MPI and GPU acceleration. So the fact is this: currently there is no as far as I know, actually, there is no MPI hook provided by a vendor yet. So as part of the development of Sarus, we had to go on and created ourselves. So we developed a hook which is bundled with Sarus and is compiled along with it and installed. This hook is able to replace the container MPI with the host libraries at runtime, allowing you to your container to achieve native performance. So what happens is that you have a portable image, you have a portable container image with a non-specific MPI, and when you fire up the container, this hook will enter the container namespace, pick your host MPI, and put it over the MPI that is already in the image. Why is this important? Because the host MPI is usually optimized for the hardware of the interconnect that you have on the HPC system. For example, think about InfiniBand, or for us at CSCS, Cray areas. All the other container solutions, for example, Singularity, do not allow you to do this. In order to have native performance from the native MPI performance from the container, you need to compile the optimized MPI library inside the container image itself. Now, this is kind of doable if you have, for example, InfiniBand, because there are a couple of MPI implementations which support InfiniBand, and VAPIC, probably I think OpenMPI as well. I'm not that, I don't know OpenMPI very well that much. But for us at CSCS, it will be a problem because we have a proprietary Cray interconnect, and we cannot outsource the Cray MPI for people to compile their own container images in. We need to be able to make that customization at runtime, and this is exactly what we are achieving with this. We rely on the ABI compatibility of the MPICH-based library, so this hook, as of now, only works for MPICH-based libraries. If you're not familiar with ABI, it's like there are two kinds of compatibilities when talking about software. One is API. Maybe you're more familiar with that. So application programming interface, meaning that as long as your functions use the same signatures, you call your functions in that way, you're able to compile them over different libraries, also adopting that standard. This is binary interface. So once your software is compiled into a binary, it can be linked against different shared libraries which respect that binary interface. So basically, when you build the image, you compile against a standard MPICH. But once you fire up the container and the hook replaces the ABI-compatible Cray library inside it, then your application just works fine, because at the binary level, it's completely interchangeable. And another thing that we like a lot is that it's completely transparent to the user. The user does not have to know anything about bind mounting stuff or having to find where their original container libraries are in order to replace them. They just need this little command line option when launching. For example, this is a OZU micro benchmarks. Is a standard set of benchmarks for MPI, for evaluating MPI implementations, and these are the results on PITSDINT of the all-to-all latency test. We go from 2 up to 128 nodes. This is the latency in microseconds for 3 different message sizes. In blue, we have a native version of the benchmark, and in red is the container. So we have pretty good consistency over that. This is for MPI. The other primary use case is GPUs. And for that, there exists a vendor available solution. The NVIDIA GPU Hook is part of the NVIDIA Container Runtime. The NVIDIA Container Runtime is an internal component of NVIDIA Docker. It is part of the NVIDIA Docker solution, if you're familiar with that. So this little program does basically the same thing that we are doing with the MPI, but it does it for the NVIDIA driver stack and the GPU device file in the container. Because in order to be portable, a container image cannot bundle the driver of the GPU, because otherwise it will only be confined to work on systems which have that specific GPU compatible with the driver. So in order to ensure portability, the driver does not go in the image. And this little body here imports it from the host, which is guaranteed to work with the hardware that is there, or the system administrator has done a lousy job. So native performance, once again, because the GPU is visible inside the container, and no required input from the user. And this is also the first example of a vendor-exclusive hook to be successfully tested on PITSDYNT. We went to GitHub, we downloaded the binary, configured it for Sarus to be able to use, and we got native performance from our P100 in PITSDYNT, which I think is pretty cool. Completely for free, no development effort in there. And once again, we have pretty consistent. This is really a small test just to validate the hook, but the numbers are there. Okay, now that we know that these hooks work and do what we want them to do, let's tackle some more interesting challenges. First, some real-world HPC applications. For example, GROMACS for molecular dynamics. This is a test case from Prace's Unified European Benchmark Suite with GROMACS 2018. Hybrid PITSDYNT partitions. So we have our Xeon and the P100 all over the Cray areas interconnect. Both hooks that I just presented are at work here, the native MPI and the GPU ones. We got I would say pretty consistent performance between native and container implementation over all the way up to 256 nodes. Moving over to TensorFlow with Horovod, because if we don't talk about AI, we are not in a post-2011 world, I would say. So this is distributed deep learning training with reference TensorFlow CNN benchmark scripts, always on PITSDYNT, and we go all the way up to 1024 nodes with some acceptable scaling profile, I would say. I'm quite happy with this data. We go over 100,000 images per second in training ResNet 50. And last, we also had an experiment. We containerized the COSMO, which is the atmospherical model used in production by MeteoSwiss for the daily weather forecast in Switzerland. So really, this model is behind all the forecasts that you see on television, radio, the mobile app, whatever. We ran an ideal benchmark for an idealized case, and also we were able to push it up to over 2,000 nodes while getting the same profile. These are different. This is a weak scalability test, and these are the lines with two different number of grid points per node. So here we have 160 by 160 grid points per node. Here we have 256 by 256. And once again, container and native performance are very close and show an identical behavior. So, conclusion. Sarus is a container engine for HPC compliant with open standards. We can achieve transparent native performance through hooks, transparent from the point of view of the user. You have minimal effort in order to enable standard container images to work on high-performance hardware. Consistent user experience with Docker. We are able to use standard, open, and upstream components on HPC systems. As far as I know, there is no other HPC container software able to use standard upstream components as part of their workflow, because runC is maintained by the OCI and is also used inside Docker, so it is as upstream as you can get. And the extensible architecture, really, we hope it encourages vendor engagement to provide their own extensions in order for their technology to be used on computers, on containers right away. And we also have the maintainability. So with that said, the only thing I think I have to explain is, where does Sarus come from? The name come from? It's a little bit weird name. So originally the project had to be called Crane, because you know cranes, containers, they move around. It seemed pretty clever. Actually, it was such a smart idea that other people had it before us. So we had to fall back on still something related to the cranes. We named it after the Sarus crane, or Antigone. It is the tallest flying bird in the world, and coincidentally, but conveniently, its colors are red, white, and gray, which are the same colors of CSCS. So corporate identity is preserved, and Michele is happy. And that's all from me.
Thank you very much. Since we are so late, and the queue for the lunch is only one, it's not parallelized, so it's only one. So I suggest people who are questions stay here in the room, and who would like already start to go outside can start, so it has a shorter queue. So either you can get some knowledge or you get something to eat. So
just to mention, for the site visit, you can leave everything here. This door is closed, and I will close this door too. So if you want to leave your laptop or whatever, it's here. The lunch is just outside where we had the coffee.
okay, let's first questions. You can start, please.
Oh, sorry.
Questions here.
Sorry.
One is, can you comment on recent advances that Singularity is doing in terms of accessibility and OCI compliance?
So yes, I am not an expert on Singularity, but I know that they have announced they say an OCI compliant runtime. The fact is that the runtime is compliant with the life cycle of the container. So the OCI specifies a life cycle over which the container has to go through. How is this created? How is it started? Whatever. And that part, their Singularity has compliance. So you can have the same commands you pass to run C to Singularity. However, there is no mention whatsoever, and I checked in the documentation, about hooks support. So from my point of view, they support a subset of the OCI runtime specification. Of course, they have already done one step in OCI compliance. In the future, they might make another towards hook support. I don't know, but as it stands right now, from my point of view, it's only a subset, while Sarus has a much more, covers much more, a much more broad part of the OCI specification.
Second question is any of this open source?
Yes, it is open source under a BSD 3 license, 3 closed license.
Where can one look at it then?
Yeah, I mean, the source is on GitHub.
Okay.
Yes, please. So, no, that is not possible at the moment, because Kubernetes communicates with the kubelet and with the pods through a gRPC interface, and that is not present in Sarus. We only have a command line interface at the moment. So we have not explored the possibility. We have not discussed the possibility as of yet, but we will see as things move forward. There is a much broader ecosystem to consider.
Okay, have a good lunch, and thank you for presenting the most green system on Earth, and it's up to you to validate this assertion. Thank you.